Thank you, Davis. It's a real honor to be here this evening. Thank you for coming out. Dr. Herbert Kroemer's semiconductor work from the 50s proposed what are now called heterostructures, but it took several decades to realize the technology to build them. He was one of the pioneers of molecular beam epitaxy, in part to realize some of the invented structures. Dr. Kroemer was awarded the Nobel Prize in Physics in 2000 for his extraordinary body of work. He is currently a professor of electrical and computer engineering here at University of California, Santa Barbara, and we're most honored to have him with us today. Please welcome Dr. Kroemer. Thank you.
If you have just heard the other 4 lectures, all are from the business and industry world. And I think this is entirely appropriate because no matter what original creative idea might have had, in order to lead to something on an industrial and economic level, you do need all the help you can get, and that help has to come from organizations like business, industry, finance, and what have you. But I'll let those people speak for themselves. So where do I fit in? Well, if you take a successful innovation and sort of trace it backwards in time, and sometimes there's maybe a very, very long time, as you have just heard. Some of my stuff dates back to the 50s. Trace it backwards in time, you inevitably run into an idea of 1 or 2 or a small number of individuals. And this is what the grassroots group. And I think a lecture series on creativity and innovation would become very incomplete if it did not also represent the grassroots point of view on this one, how it all got started, the early phases of something like this. And I think this is where I fit in. So I decided to give myself a title to my talk. So I call it From Ideas to Applications and Back. Some grassroots observations and lessons. Now, new ideas in technology typically draw on new developments in technology, sometimes very new developments. And that immediately leads to an interesting question. Let us take applications here, let us take technology here. Which is the chicken and which is the egg? So this is a key issue. And let me tell you right away where I stand on this one. It's a question that has occupied my own interests for many, many years. And if you look at the history of technology, you discover very quickly that you can state something that I call Kroemer's lemma of new technology. And it says the principal applications, notice this is emphasized, of any sufficiently new and innovative technology always have been and will continue to be applications created by this technology. And I fully realize that this picture would be much sharper if this were a conventional view graph. But this is the kind of modern hardware that we unfortunately have to put up with. Well, what I mean by principal applications, of course, I mean applications, not something casual, I mean that which actually makes the whole thing tick, the important stuff. And I'm talking about sufficiently new and innovative technology. So I'm not talking about some minor improvement. I'm talking about something that really is totally new. And the idea is that these principal applications will be applications that will be created by the technology, and this has been that way in the past, and this is likely to be that way in the future. So we are not talking about doing something a little bit better that we already can do acceptably well. We are talking about doing things that we couldn't do at all, and often things that we hadn't even thought about doing. One of the difficulties in predicting future applications is that it is in fact applications that have to be created by the technology. That prediction of the future is not easy, and history shows that in many, many cases these future applications were not predicted, and in fact could not have been predicted. And so what this means now is something else. It means if you're looking at a new piece of technology and get asked the question, well, what is it good for? There's a great danger that the people who ask you, what is it good for, will say, all right, you cannot give me a good answer, what is it good for, let's therefore forget about it. rejecting new technologies just because you have not yet been able to identify applications. You reject them because of the lack of identified application. This does not advance progress, it retards it. Because it basically blocks the path to those things that will ultimately emerge to be the important ones. And this is a lesson that is not widely understood, and this is something that I have been saying over the years quite a few times, and I take whatever opportunity I have to say this, and this is one of them. And I feel that this is something that is important for you to know, particularly for those of you who might find themselves in this kind of business of innovative and creative technology. You might have to answer questions like I had to answer them during my career. What I want to do throughout my talk is basically two things. I want to give you a set of 4 examples that support this idea of the principal applications being applications that get created by the technology. And after I'm through with those, and I could give more, but I don't have that much time. After I'm through with this, I will do something that I've never done in the past. Normally at a professional conference, I stop at that point. There's no point telling people about me and what I myself have experienced. They are my colleagues, they have gone through the same kind of stuff. But with a group of students, I think this is different. I think many of you are likely to confront situations like I have confronted them. And it might be just a little bit useful to know that you're not the first ones to get confronted by these questions. And so I'm going to talk about myself, not because I'm special, but because I'm probably quite representative of what some people in this business encounter. Well, here are my 4 examples. The first one is the transistor itself. The second one is liquid crystals. Then there's the semiconductor laser. And then there's nuclear magnetic resonance. And I will actually present them the last 2 in opposite order, because by talking about the semiconductor laser last, that leads more naturally to the topic where I want to talk about my own experiences, what led to these ideas. So let us start with the transistor. When the transistor was invented, and some people would say it was discovered, it was universally viewed as a replacement for already existing devices. The telephone company, for example, and they were, of course, the originators of the transistor, had a very strong interest in simply replacing electromechanical relays which connected different lines to each other, to replace them with electronic switches. And they had other applications in mind. The electronic industry at large universally viewed the transistor as a replacement for electron tubes. And they treated it as such. Not necessarily in their research laboratories, but in their whole strategy and in who was put in charge of the development in the product stage. And they invariably put it under the jurisdiction of those parts of their organizations that were responsible for electron tubes. Because after all, it went ultimately to the same customers. Why not have one organization handle it all? And that was the kiss of death. And this is, in the last analysis, the reason why none of the old mainstream electronics company played any significant role whatsoever in the future evolution of the transistor. It was a kiss of death for 2 reasons. First of all, an industrial manager who is responsible for the color of the ink at the end of the quarter and who doesn't want to see red ink is naturally reluctant to spend a lot of his funds or her funds on a research where it wasn't quite clear what would come out of it, where it cost a lot of money. But perhaps more important, if you put somebody in charge of a development, somebody who made his career on the basis of his achievements in the technology that you want to replace, then this person is not likely to believe in this replacement. So if you have a new technology and you want it to succeed, for heaven's sake, put somebody in charge of that technology who is 100% responsible for this technology and whose professional career will depend on making it a success, rather than obstructing the technology because it obsoletes what he himself became known for. Well, anyway, what really happened, of course, with the transistor, yes, electron tubes eventually were replaced. For heaven's sake, in the 70s, even the TV sets became transistorized. It had become cheaper to do it with transistors. It had been technologically possible many years earlier. But the transistor really did was something altogether different. It created the modern computer. That is a huge achievement. Now, there were computers, of course, back in the 50s. Yeah, they ran off electron tubes. This is not the computer I'm talking about. It's the computer that you and everybody else has in their homes. It's the computer that has totally changed our civilization. That is the device that the transistor created. But that was not a straightforward path. Because the transistor that was invented or discovered in December 47, I think it was a germanium-based bipolar transistor, whereas the transistor that makes today's computers is a silicon-based complementary MOS transistor. And some of you probably know what that is, and those who don't, simply be aware that these are two completely different animals. In fact, the history is quite interesting. The bipolar transistor was actually an accident. It was discovered as a result of a failure to achieve a field effect transistor. They originally wanted to make a field effect transistor in germanium, and the darn thing didn't work. And the reason it didn't work, they found this out very quickly, was that the interface between the gate dielectric and the semiconductor had unavoidable defects. And when you change the voltage on the gate in order to change the current flowing through the device, in reality, you simply change the electron occupancy of the defects, and the current was unchanged. And there was no reason to believe that this would in any way be better if you switched from germanium to silicon. In fact, many of us felt that silicon would never make it because you could never get rid of that stupid oxide. And it was only later that people discovered, hey, this oxide is the best part of silicon. Initially, this was discovered because it served as a useful passivation. That was long before it was used as a masking technique. It served as a useful passivation of the junctions that were exposed to the surface. And it came as a big surprise when people discovered that if you used thermally grown oxide, in other words, not deposited oxide, but stuff that you actually had grown by exposing the silicon to a particular kind of oxidizing atmosphere. There had to be a certain amount of water in the atmosphere for it to work right. That in that case, you ended up with an interface that didn't have the defects. And that was making field effect transistors possible, and it ultimately was making CMOS possible, and that was ultimately making the computer possible. And anybody who claims that this could have been predicted in the early days of the transistor doesn't know what he or she is talking about. Because if it could have been predicted, it would have been predicted. So this is example number one. My next example is the liquid crystal. Well, liquid crystals have been around for a long, long time. And for most of their life, they were totally useless other than as a scientific curiosity. But the liquid crystal ultimately created the laptop computer. It created the portable computer. Because now you suddenly had a display that would go hand in hand with something that you could carry. And you certainly wouldn't want to use a cathode ray tube for that. And it took a long time, incidentally. The first liquid crystals were pretty pathetic. In fact, the first handheld calculators couldn't use liquid crystals because they were so bad. They used light-emitting diodes in the red, which were basically battery eaters. Well, but today's laptop is, of course, operating on liquid crystal displays. But this is, again, an interesting development. You might assume that those companies that were in the computer business and who had cathode ray tubes for displays would recognize, hey, here's an alternate way to make a display, and maybe you could use a portable. Nothing whatsoever like this happened. They were so totally obsessed with their cathode ray tubes that the entire liquid crystal display got done by organizations that had no investment, no stake in cathode ray tube displays. Largely to a large extent Japanese companies. But now something interesting else happened. So you see, once you have a technology that has created a new application of its own, then it becomes very tempting to use this technology to do something like replacing existing applications, because you have developed the technology to a level that you certainly can compete with the existing applications, compete both in performance and ultimately in cost. And so, well, today still a number of computers, many computers still have cathode ray tubes as display, but this is simply because they were bought a few years ago. The cathode ray tube, for all practical purposes, a computer display, is dead. Within 2 years, you will probably not see many of those. Certainly within 2 years, they will no longer be manufactured perhaps as replacement parts. You can buy them at eBay probably as old parts. But now once you have done this to desktop computers, there's nothing to stop you from going the next step, to go to TV. And I think we will see the same thing in TV. The development is already underway. So the competition is no longer a competition between cathode ray tubes and liquid crystals. It's a competition between liquid crystals and plasma displays. And if I would bet my money, I would bet it on the liquid crystals, not on the plasma displays, for reasons that do not belong into this talk. So again, we have here an example of a new technology that created a whole huge range of applications. And once successful, now invaded the territory that it could never have invaded without first being successful in its own area. All right, nuclear magnetic resonance. Most of you probably don't know what that is. It was discovered in the 40s. Well, you put some atoms into a magnetic field and you tickle them with a signal of the right frequency and something happens. Bloch and Purcell, Bloch at Stanford, Purcell I think was at Harvard, got the Nobel Prize for this in 1952. And nobody ever was thinking about any applications. Well, it so happened that a small company up in the Bay Area in Palo Alto, Varian Associates, was founded by a bunch of people who were basically spin-offs from the Stanford physics department. And they knew Felix Bloch, and they came up with the idea that, well, maybe we could actually market an instrument, a commercial instrument for magnetic resonance. So they hired a consulting firm, did the market research. And I got to know Russell Varian later because I actually joined Varian Associates as an employee. I got to know Russell Varian later, and he told me what happened. Well, they came back that the world market would be good for about 6 or 8 instruments, and after that it was over. And Russell Varian was smart enough to realize a foolish thing when he saw one. He was absolutely convinced that this device would have applications, and they went ahead anyway. And it was a stunning success, because very soon it was discovered that the signal that they were detecting in magnetic resonance depended very slightly on the bonding environment of the atoms in the molecules. It became a powerful analysis tool for organic chemistry. It didn't play much of a role in inorganic chemistry. But that was only the beginning. It also created something altogether different, medical MRI, magnetic resonance imaging. And which is now a non-invasive, non-destructive technique to look into the human body and to get details that are far beyond what you can get with X-rays. Anybody who has ever been through this one, it's an interesting experience. And the detail that you can see is absolutely spectacular. It got the Nobel Prize in Medicine last year, not the year before. But now again we are running into a case of synergism. In order to be able to go from an ordinary magnetic resonance spectrometer to an instrument that looks at the human body, you had to have magnetic fields that were fairly strong, typically on the order of 1 Tesla, of a volume sufficiently large that you could put a human body into it. And you're not going to do this with copper solenoids for magnetic fields. That requires superconductor technology. So here we see that 2 completely separate technologies got together. Both were needed for this new thing, and this kind of synergism is a typical example of what happens in the step from new technology to new applications. And if there's anything that is totally unpredictable, it's this kind of synergism. Well, I'm finally getting to my own favorite topic, the semiconductor laser. And as you heard, I played a role in this one. Well, let me keep this away, what it actually did. This whole thing started in June of 1962 at the annual Semiconductor Solid-State Device Research Conference, which in that year was held in Durham, New Hampshire. I was there. I routinely went there. And that was the conference where people from many, many industrial laboratories and a few universities were for the first time demonstrating gallium arsenide junction lasers. And it was kind of interesting. I was working on other things. I wasn't particularly interested in lasers, but I listened. Of course, nobody had any idea what those things were good for. And it was very clear that these things were not likely to be good for anything for the following reasons. First of all, they only worked in the infrared. So any applications in the visible were out. Although this could conceivably be handled by using different materials, and it was eventually handled by using different materials other than gallium arsenide. But at least as important was the following. These devices did not work continuously at room temperature. They worked only with very, very short pulses separated by large intervals of rest, a low duty cycle. And well, things were a little bit better if you went to liquid nitrogen temperatures, but this is not a practical device for industrial innovation if it needs a liquid nitrogen temperature. That's a laboratory curiosity. Well, I was aware of this one, but didn't pay any particular attention. But a colleague of mine, who was also working at Varian Associates, I was working at Varian Associates at the time, who was also working at Varian, became very interested. He had been at the same conference. And it must have been in March of 1963 that he gave a seminar at our company on this subject. It was an absolutely beautiful presentation. And he explained why this wouldn't work at room temperature. And so let me now switch format here. Let me show you the essence. This is much more recent. That was not done back in 63. Let me explain to you why it wasn't supposed to work. Let us assume you're having a gallium arsenide p-n junction, a homojunction, no different semiconductors. And let's, of course, as you know, I hope, a p-n junction in a semiconductor, there's a potential difference between the p-type side and the n-side. It's basically a barrier there. And if you apply a forward bias, you can lower this barrier. And let us assume you have just applied the right amount of forward bias to the p-n junction, that the barrier has just disappeared, so that the bands are flat. So on one side you have electrons, on the other side you have holes, and the electrons flow from the left to the right, and there are holes from the right to the left, and you now have a region in between where you have both electrons and holes, and these electrons can then recombine with the holes, and that process emits light. But in order for to get a laser, you do not just need a few electrons here and a few holes down here. You need a lot of electrons and a lot of holes. Basically, the lowest energy level in the conduction band has to have a higher occupation probability than the highest energy level in the valence band. And that is not very easy to achieve. And one of the reasons it's not easy to achieve, well, there are two reasons. First of all, you will never have as many electrons here as you have electrons in the reservoir. But the real problem is that those electrons escape very quickly. And it is basically impossible to obtain this kind of population inversion that is necessary for a laser in steady state. And in fact, even if you're not interested in the laser, if you simply want to have a bright light emitting diode, you'll run pretty much into the same problem. At low temperatures, it's a little bit different. But again, this is not a practical device. Anyway, Saul Miller, my colleague, explained that people had looked at this one and they had concluded that therefore it was fundamentally impossible to get a semiconductor laser to operate continuously at room temperature. Well, as soon as he was finished, I just blurted out and said, but that's a pile of... Now, inasmuch as I know that this will go on TV, I'm not allowed to use that word here. But let me assure you, it starts with a C and has 4 letters. Anyway, I said, all you have to do is to put a wider energy gap on the outside. So now the electrons run into a barrier and they can no longer flow out. The holes run into a barrier and they can no longer flow out. So we have achieved electron and hole confinement. But that's not all. If you increase the bias voltage a little bit more, you now create a bucket here where you can collect electrons. And in fact, it is possible to have a higher concentration of electrons here than in the reservoir. So you no longer need those astronomical doping levels. The same down here. And what was previously impossible suddenly became easy. And that is the story, the idea behind the double heterostructure laser. It's kind of intriguing to realize that I came up with this idea that basically within a minute after somebody had told me there was a problem we're solving, the solution was obvious. I'll tell you later why it was obvious. Anyway, so what did the laser do? Well, the laser did a lot. But before I get to what the laser actually did, let me tell you what I ran into. The first thing is, you wrote this up a paper and you submit it to the proper journal, which is Applied Physics Letters, where it gets rejected. Well, I was put under pressure not to fight the reviewers, but to send it to the proceedings of the IEEE, because in those days they published anything. And sure enough, they did publish it. But of course, those people who were working in this field were not reading the proceedings of the IEEE, so that was bad advice that I got there. So be prepared for getting bad advice. Do not publish in journals that the people you want to address don't read. But the next step was, all right, there was no technology inside to actually do that. Well, all right, so you develop the technology. Now, my ideas of what that technology might be were very, very naive by hindsight. They wouldn't have worked. But that wasn't the answer that I was getting. I was told it made no sense whatsoever to develop this technology because this device could not possibly ever have any practical applications. In order for a laser to be useful, it either has to have a very clean spectrum, like the helium neon laser, you can do with it the things that you do with the helium neon laser. Or it has to have lots of power, like the carbon dioxide laser, so you can drill holes through bricks. That semiconductor laser promised neither a clean spectrum nor a lot of power. Therefore, it was demonstrably useless. Well, you see, what they did is they compared this laser with other lasers. Nobody asked the question of, well, what would it be good for? Is there anything it would be good for? And of course, the story is it was good for a lot of things. It created, and that was the first practical application. It took many years. It took almost 20 years from the original idea. It created the CD. It made commercial CD players possible. It therefore created the CD. So this is a very odd combination. I wasn't out to create CDs. I hadn't the foggiest idea what the applications would be, but at that time in my career, I was already convinced that such a new phenomenon was bound to have some application. And typically what happens is the person who starts with the technology thinks differently from the person who has the applications. The person who starts the technology has a solution in search of a problem. The applications person has a problem in search of a solution. We need to get those people together. And those people eventually do get together, and that is where the new applications come from. Well, perhaps more important than this frivolous application of the CD is fiber communications. In those days, electrical signals, like the telephone signals, were transmitted through coaxial cables. And everybody was painfully aware that this was a process of limited capability. Coaxial cables are too lossy. They could never carry the bandwidth that we wanted to carry. And there was, in fact, a lot of work going on in industry to look for other forms of signal transmission. And there were a few people who looked at optical fibers. But of course, they were poo-pooed just like I was poo-pooed because there was no proper light source to use the optical fibers. Well, the laser and the optical fiber came together. Another example of this beautiful synergy. And let me assure you that without this combination, we would not have the internet. Now, some people might think this would be a good idea not to have the internet, but I'm not going to advocate that one. Well, eventually, of course, we again had this backdoor invasion. Once this laser technology had been developed for its inherent applications, for applications that justified the development, it became attractive to use it for other things. And we are now seeing it in the form of light-emitting devices that are not lasers, that are ordinary light-emitting diodes. And they are now competing very, very heavily with tungsten filaments. And I make the prediction that within a few years, all of those applications where you want colored light anyway, the tungsten filament will be dead. You look at traffic lights in Santa Barbara and you see there are already, most of them these days are LEDs, although there are still a few with light around that have light bulbs with a colored glass in front of it. If you see a really sick-looking green, that's a colored glass with a light bulb behind it. If you see a green that really says green, then this is a bunch of LEDs, and you can typically tell them because they consist of individual pixels. So this is then the story of my 4 examples that I wanted to give you. Let me sort of summarize it. See, I go back to that other view graph format. Back to Kroemer's lemma, the corollary. What this really says is the path from science and technology to application is an opportunistic path. It is not a deterministic path. So, and I've always considered myself an opportunist. An opportunist is, I know this is supposed to be a dirty word, but I think an opportunist is a person who looks for opportunities. If you want to get in research, be opportunists, because this is where the interesting things really happen. Well, let me now turn to the other half that I promised you. People ask me, well, how did you come up with this? How did this idea of the double heterostructural laser simply drop from the sky all of a sudden in a minute? And the answer is, of course, no. It's a classic case of the prepared mind. See, what I had been doing for many years before then, ever since around you see this happened, this original laser discussion happened in '62. I had been working since the mid-50s, since the early 50s, on transistors. And in the work on transistors, I realized that some of the transistor performance could be dramatically improved if you didn't use a single semiconductor, but if you use two or more semiconductors, so-called heterostructures, although in those early days we didn't call them heterostructures. So let me tell you how that part started. Immediately after my PhD, a PhD incidentally in theoretical solid-state physics at the University of Göttingen, I was hired as the theorist in the semiconductor research group of the telecommunications laboratory of the German Postal Service. Now, you would not associate transistors with the United States Postal Service, but in Germany, and for that matter, in most European countries, the telephone system is under the jurisdiction, or it certainly was in those days, under the jurisdiction of the Postal Service. And so, naturally, the German Postal Service had a telecommunications research laboratory, sort of a mini Bell Labs. It was very mini. It was a small lab. Its function was, to a large extent, to look ahead at what was about to happen, look ahead at the future. And in our case of semiconductors, it was likely that semiconductors and transistors were going to play a role in communications. And our job was basically to look ahead, and to look ahead over the long term, not just what was going to happen next year, but what was likely to happen a few years down the road, because major investments in technology were influenced by this kind of information. So it was inherently pushed the long term. Well, one of the problems that the early transistors had was they were hideously slow. And so I was looking at, first of all, trying to understand what made them slow, and secondly, what can you do about it? And the first thing I did was I misidentified the principal reason for why they were slow. I actually identified something else, which was a minor reason, but which turned out to be amazingly fruitful. Sometimes you can have good ideas for the wrong reasons, and it was one of them. I decided one of the reasons they were slow, and it was a contributing factor, was it took too long for the electrons to get from the emitter to the collector. So if you had a force that would push them so they wouldn't rely on diffusion. Diffusion is a form of random walk. You just accidentally get there. If you actually would have a force that would push them, the transistor would be much faster. It would be, it just wasn't the dominant reason. But anyway, that was what I was pursuing, and it turned out to be amazingly fruitful. And my idea was the following. One of my ideas was the following, that, all right, one way you can introduce a force was to use a non-uniform energy gap in the transistor. So here was the idea, let's not use one semiconductor, let's use a mixture of semiconductors with a position-dependent composition. And so the idea was, let's use silicon at this end, and germanium at this end, or some mixture, some composition, not all the way 100 to 0. And if you now dope, this is a PNP transistor. In those days, all transistors were PNP transistors. If you now dope the base heavily, then the conduction band will be flat, but the valence band will have a slope, and a slope means a force. And so basically what happens if you get holes down here, holes behave like bubbles in water. They try to rise to the top. So the holes would be pushed by the slope to this side much more rapidly than would otherwise be the case. If you're not interested in PNP transistors, if you're interested in NPN transistors, you simply flip that view graph over. In the laboratory, this is not quite as easy, but in a view graph, it is. So, in fact, most of today's transistors are NPN transistors. Well, so here was a new concept, obviously crazy. And when I talked to that one of my collaborators, who would ultimately be the poor guy who would have to build this one, he says, no way, Herb. Actually, he didn't call me Herb. This was very formal. No way, Dr. Kroemer. I have no technology in sight that we can do this. The most I might be able to do would be to put a silicon emitter on a germanium base. But he and I immediately realized that this would not do the job, because if you put the silicon emitter on the germanium base, now the slope would be gone and the force would be gone. Well, on the way home, I sort of wondered what actually would happen if you did this one. Because I realized that what this meant, if you put a wider energy gap here, that this would raise the height of this barrier here, whereas this barrier was a lower barrier. And when you go through the details of the design of a transistor, you discover that you can dramatically change the doping levels in the transistor. You can dope the base much more heavily. And the bottom line was that this was an advance in its own right, would increase the transistor performance for completely different reasons. And so these two forms of transistor, they later became heterostructure, called HBTs, or heterostructure bipolar transistors, were the idea that I sort of came up with. That was in 1954. Well, I actually put this into a publication that I wrote in 1954, but it wasn't followed up. I didn't follow it up. There was really no technology. But I picked the idea up again about 4 years later. 4 years later, I was at RCA, had come to the United States. It was working at RCA Laboratories in Princeton, New Jersey. A wonderful laboratory, incidentally. So I had been hired there. So you expect that you're being told what to work on. No, I was given a desk and say, well, look around and see whether you find an interesting project you want to work on. Wonderful. And I found lots of interesting projects. And in 1957, in early 57, I decided to look again back at this idea of a graded gap in a transistor. And I suddenly realized that this was far more powerful than simply making an improved transistor, that it had much more capability. And so let us assume, I lost my shadow cardboard here. No, here it is. Let us assume we just have a piece of silicon and we apply an electric field. Could be germanium, doesn't have to be silicon. Well, that's interesting. What happened? Oh, there. I'm blind. Sorry. This really looks sad. Well, so you have slopes in the band, and you have a force driving the electrons from the left to the right. You have a force driving the holes from the right to the left. The two forces are exactly equal in magnitude, but opposite direction. But it's ultimately the slope that is important. Now, if you vary the energy gap, you can do something altogether different. You can have a situation where the force of an electrons and holes is in the same direction. And this is, of course, something that is fundamentally impossible to achieve with electric fields alone. So here was it's a quantum mechanical effect, basically. So here was a new force. And it was very obvious that we now had broken the link between the force on the electrons and the force on the holes. And we had, to some extent, separated those two forces from the electric field itself. The electric field was still there, but it was the slope in the band edges. And at that point, I realized how tremendously powerful this concept was. And you will not be able to decipher that one. Oh, maybe, yes, maybe you are. In a homogeneous semiconductor, the band slope under an electric field is the same for all bands, and as a result, the forces upon electrons and holes are equal in magnitude and opposite in direction. This is not the case for a varying energy gap. Anyway, let's move on. Electrical forces in uniform crystals can never do this one. I introduced the concept of the quasi-electric field. This is why we call these forces quasi-electric forces. They present a new degree of freedom for the device designer, which enables him, in those days all device designers were male, enables him to obtain effects with the quasi-electric forces that are basically impossible to obtain with ordinary circuit means involving only real, in quotation marks, electric field. This is quite possibly the most important paragraph that I've ever written in my life. It is the central heterostructure design principle, and all heterostructure devices that subsequently emerged follow this idea in one way or another. I only made one mistake. I published it. It was done at RCA, and they insisted that I publish it in the RCA review, but who on earth reads the RCA review? Well, one person did read it. Jerez Alferov, who shared with me the Nobel Prize in 2000 for the work on heterostructures. So maybe it wasn't all that wasted. So anyway, this is basically the end of that part of my story on how this concept, why it was so obvious to me when I was confronted with that laser question, why it was so obvious to me that using heterostructures was the answer. It was just another case of the same idea that it works so beautifully in the transistor. And in fact, those transistors have since then become very, very important. Most of your cell phones probably contain some of them. They play a large role in telecommunications technique in high-speed electronics. Well, I still have a little bit more time left. And so I mentioned to you that I had received a PhD in theoretical solid-state physics and ended then up as a theorist at the German Postal Service Laboratory. Well, I should perhaps tell you a little bit about my experiences as a PhD student in Göttingen, because these experiences were absolutely invaluable. They really had a tremendous influence on me, and I want to tell you about this one. I came to Göttingen in the third semester as a physics student. I had spent the first 2 semesters at the University of Jena in East Germany. The political suppression in East Germany was becoming pretty unbearable. I spent the summer in 1948 in Berlin, which was at the time of the Berlin blockade and the airlift. And I decided I'm not going to go back to East Germany, and I had a recommendation from a professor from Jena to talk to somebody in Göttingen, and even though the odds of actually being accepted in Göttingen seemed negligibly small, I tried it anyway, and I was lucky. I remember one exam question. So I showed up there, and all right, so some professor had a friendly chat with me, and I very quickly realized that this was not just because they had nothing else to do and wanted to be social, but I was actually going through an exam without knowing that it was an exam. And Professor Powell asked me, one question was, well, Mr. Kroemer, you know that a mirror interchanges left and right. Yes, I know that. Well, where does an interchange top and bottom? Well, he was very happy when I gave him the right answer, and I let you figure out yourself what the answer is. Anyway, so I became a student in Göttingen. And it was a wonderful university. In German universities in those days, there were not those endless rigorous course requirements. You have to take this, and you have to take this, and you have to take this, as we do. And I never liked these rigid course requirements. There were certain exams you have to take, and there were certain documents that you had, certain performance documents that you had to deliver. But you were pretty much free to structure your education around those minimum requirements. And there was one class of courses that I absolutely loved. And there was sort of a mixture between special topics and group studies. Typically what happened was that one of the instructors decided, hey, here's a subject matter on which I want to know more. And so rather than going through all of that himself, he simply picked out what were the most important papers in the field and then assigned those papers to the attendants in the seminar. And these were real research papers. And you had to make a very, very good presentation. The quality of your presentation was measured by how much the instructor himself learned from your presentation. So you were not getting any help there. You had to do it. And these were real research papers. This is an altogether different world from simply taking classroom lectures from a book where the guy who wrote the book never contributed to the research. So you learn how it was done. So it was an instruction, it was valuable for the instructor, and it was valuable for the student. Because those of you who have ever served as TAs probably know that the best way to learn something is to teach it to someone else. This is far better than simply absorbing it passively. Nobody applauds. So anyway, it was a wonderful experience. Furthermore, those instructors typically picked their research students from their seminars. If, for example, you wanted to study under Professor Becker, who was the head of the Institute of Theoretical Physics at the University of Göttingen, and went to Becker, you almost certainly were being told, well, that's kind of interesting, but I know nothing about you. Why don't you first participate in the seminar of theoretical physics for a year, and then we'll talk. And in fact, I participated in the seminar of theoretical physics. I loved it. And both my master's dissertation and my PhD dissertation grew out of talks that I had presented there. And I want to tell you a little bit about that PhD talk. It was during the second semester of that particular year. I was assigned, it was a course on semiconductors. Professor Sauter actually handled the course. Professor Sauter was not a regular member of the faculty. He was a refugee from East Germany. He had been a professor in one of the eastern provinces that got lost after the war. And he sort of was simply taken on as a guest in Becker's Institute. The two knew each other. They were good close friends. And Sauter participated very actively in the seminar. And Sauter decided to spend a year on semiconductors. He had no background in semiconductors whatsoever. So why did he do this one? Well, he needed some extra money, I think, and so he had been hired as a consultant in the semiconductor field by one of the German electronics companies. He knew certainly more than the people who were hiring him as a consultant. But Sauter was a wonderful universalist. He was a person who was absolutely convinced that any self-respecting theorist, if confronted with an interesting and challenging problem, would have the ability to acquire the material necessary to be a productive contributor in a matter of a few months, and within a year he would be on top of the field. And it was true. He did that. Becker was the same kind. And this made a tremendous impression on me and rubbed off on me. It contributed, incidentally, to my not taking regular courses all that terribly seriously. I decided if I someday have to know Bessel functions, well, then I'll get down on my knees and learn Bessel functions, but I'm not going to clutter up my mind with this or with any other things until I actually need them. It worked like a charm. I never took a course in electromagnetic theory, for example. Can you imagine? Yeah. Well, anyway, Sauter then gave me a talk, assigned to me a paper by Bardeen and Bratton on the physical principles of transistor action. This was the first great paper in the Physical Review where they put together all of those things that they had learned about transistor. It was a wonderful paper to read. And there were a few puzzling problems in the paper. In those days, transistor didn't mean a transistor with p-n junction. It meant a piece of germanium. You poked two needle contacts, steel or phosphor bronze, onto the germanium surface, as close together as you could them, typically 100 microns. You biased one of them positively, and that injected holes into the semiconductor. You biased the other one negatively, and that collected the holes. So you had an emitter current, you had a collector current, and the puzzle was that the collector current was bigger than the emitter current. So there was something funny going on. And the paper made some suggestion that it might have something to do with space charge, but they really left it open what was going on. And even those suggestions that it didn't really make a great deal of sense. And at that point, I couldn't resist speculating. And so at the end of my talk, during that seminar, I made a suggestion about what the space charge mechanism might be. And I said, the field, electric field in the collector is very, very large. And furthermore, the conduction band and the valence band of the semiconductor, they have a finite width. So what would happen if there were no scattering events? Well, what would happen in this case, if there were no energy losses, then the electron, or the hole, whatever the case might be, would oscillate back and forth in that tilted band. And in fact, there would be no current flowing. You actually needed energy losses in order for a current to flow. And the larger the electric field, the slower would be the velocity with which the electrons would propagate. And that, of course, if you cram a fixed current into this piece of semiconductor, then with increasing field, you would have an increasing space charge. This space charge would then enhance the field at the collector to semiconductor interface, and it's this enhancement of the field which would then create the extra current. And Sauter loved it. He immediately suggested that we make this into a PhD topic. And so out of this crazy idea came a PhD. And it turned out later on that this didn't really work. That was not the reason for this funny ratio between collector and emitter. But the underlying physics of this oscillation showed up many, many years later as the physics of transport properties in semiconductor superladders, where it plays an important role to this day. Sauter was a very interesting man. He had his own ideas about what he wanted to do as a research advisor. He was always available if I had a question. I never had to wait, make an appointment. He was available. And he would try to answer this question, but he absolutely refused to make suggestions of what I should be working on. In fact, his whole idea was, the idea of judging his students was to observe them and judge what they would do on their own initiative. And he observed very closely. And it seems that he was quite happy with my dissertation. And he had the idea that for him a PhD is simply a certificate that says, this person, I certify that this person has the capability to handle difficult projects independently and without supervision. He knows how to evaluate the possibilities that this might be workable. He knows how to acquire the necessary resources. And once he had convinced himself that the student was ready, he wanted to get rid of the student. He said, all right, here's your degree, get out. In fact, it was difficult to get a PhD from him that would last longer than 2 years. If it lasted longer than 2 years, you would never get it, because he would say, go somewhere else. It took me a little over a year, and I had my PhD a few weeks before my 24th birthday, which I think some of you are envious. I remember about a month after I got the Nobel Prize, I was invited as a speaker at a workshop that the German Ministry of Education had set up, not in Germany, but in Palo Alto at Stanford. All right. It tells me to shut up, but I'm almost finished. At Stanford, where they had collected something like 150 German postdocs spread all over the United States. And there was for some ideas exchange. And somehow this fact of my early PhD got mentioned. And and one of the guys just stood up and said, "But at 24, you didn't know anything yet." I was tempted to answer, well, that didn't prevent me from getting a Nobel Prize, but I felt that was kind of rude, so I didn't do that. I simply said, listen, you are absolutely right. My subject matter knowledge was zilch. I had really very little in the way of accumulated subject matter. But that isn't really what matters. I knew how to acquire the subject matter when I needed. I understood the methodology of research, and that is so much more than an accumulation, worth more than an accumulation of facts. And so there were other aspects of Sauter, and it took me years to realize how important he actually was for me. For example, let's assume you came to him with a problem in physics. You had an idea in physics. And with a slight tinge of sarcasm, he would then ask you, well, this is kind of nice, but you ought to be able to formulate this mathematically. All right, you'll learn how to formulate your physical ideas mathematically. But you may come to him with a mathematical solution of something, leading to a curve that had certain characteristic features. Well, same sarcasm, but that's just a part of math. Why does it have this? Because why does it look the way it does? Why does it have a maximum there and a null there and something else? And if you told him, well, that's just the way it comes out of the math, you had to find a different research advisor. He was through with you. You had to be able to explain in physics terms why the math, at least qualitatively, you had to understand qualitatively why the math, why it did come out of the math. And if you'd gone through this cycle a few times, you'd get the message. And he was a superb mathematician, but he also absolutely insisted that you tackle a problem with the simplest math accessible, and you make, at least at the beginning, as many simplifications in the physics as you could in order to simplify the problem even further. So the idea that you first solve it in all generality and then look at special cases, that's not the way to do research, that's not the way to learn it. If you cannot solve the simple problem, you will not be able to solve the complicated one. But if you can solve the simple problem, it will teach you an awful lot about what is going on. And then you add on the complications later on. It's sort of a form of intellectual perturbation theory. So anyway, this is the story, and that's a good point to stop. As I told you, I had this lemma of new technology. Let me express at the end it in somewhat different way that somebody else has said. You see, you're likely to be told nowadays by many funding agencies to concentrate on strategic research. And just because they use the word strategic, it sounds like it's something awfully important. Well, David Merman, who absolutely often writes wonderful editorials in Physics Today, in 1999, put down this absolutely gorgeous put. I'm awaiting the day when people remember the fact that discovery does not work by deciding what you want and then discovering it. Keep this in mind. Well, obviously the work that I did had become important. And during the 90s, people periodically told me, oh, Herb, you will get the Nobel Prize. To the benefit of my mental health, I never took that seriously. Even though it was clear around 1996 that my name had been kicked around, but every year they get hundreds of nominations. And if you look at the history of the Nobel Prize, I knew that what the rules were, that you were not going to get the Nobel Prize in applied physics or technology. Nobel Prize was for fundamental discoveries, and I had not made any fundamental discoveries. And so those people who expressed their opinion about that one, I simply dismissed it. I tried to be nice to them. I dismissed and said, oh, they just don't know the rules. But I didn't realize they had changed the rules. Now you see, the Stockholm Nobel Committee, they meet in the morning and someday in October, and everybody knows what that day is. And of course, they want to go to lunch at 12 noon, and 12 noon by California time is 3 o'clock in the morning. And then this is the end of my story. Who in the world would be calling at 3 o'clock in the morning? And so, thank you very much.
Thank you, Dr. Kroemer, for speaking with us tonight. I'd now like to move into a quick question and answer session. There will be one mic over on this side of the room, one on the other with Davis. If you have questions, please direct them to us. You'll speak into the microphone so we can get it on tape. Looks like we have one here.
Professor?
Yes?
You did a lot talking about your previous work, but nowadays you work a lot on electron spin, the way I understand it.
I don't. No.
You don't?
No. Spin is a four-letter word. I don't work on spin.
But
I don't know what gave you the idea. No.
Okay, could you comment then just briefly on some issues with that we still have to cover, or some hurdles we have to pass before we can see a truly quantum computer?
Oh boy, I don't know the answer. And you have to occasionally have the courage to admit that you don't know the answer rather than trying to fake one. The quantum computer is an absolutely fascinating concept, and if it can be done, it will be done by somebody who believes in it, not by somebody who says it can't be done. It certainly has already tremendously impacted our understanding of quantum mechanics. But it's not clear to me whether we will, or when we will have a quantum computer that actually does the things why people are interested in it. However, if you ask me whether I view this, despite the uncertainty that I'm expressing, whether I view this as a valid research topic, the answer is absolutely yes. If you want to do research, by all means do it. But be aware that you're undertaking a high-risk project. But what else is new? Did I answer your question?
Other questions?
I have a question for you, Dr. Kroemer. I was wondering, at what point in your mind do you realize that proceeding in some certain research is going to a dead end? And not so much in a technical standpoint, because a lot of people in here are going to be businessmen and women. At what point in their mind would following a business idea, personally, how do you know that?
I didn't quite get your question. Certainly, I have worked over my career. I only told you some of the good things. I've worked during my career on many things that didn't pan out. The dumbest reason for continuing work when it looks like it doesn't pan out, the dumbest reason for continuing is because you've made the mistake of having started it. And so you should never hesitate to dump it. I once dumped a major research project that had taken a long time. I basically dumped it over lunch. In the morning I had done some experiment that, again, I ran out of excuses of what might make this project work. And I thought about it over lunch. In the afternoon, I cleaned up my desk, disposed of all of that stuff that I had accumulated in this field, went to my supervisor, to my boss, and says, Harwick, it was at RCA, Harwick, I decided this is not going to work out. I want to stop it. He just grinned and says, all right, Herb, we knew we would come to this conclusion because we had been failing for this for some time. But we wanted you to come to this decision yourself. You were right. And this has happened before. If you have worked on something and it doesn't work out, one piece of advice I give you is it sounds sarcastic, but I'm actually serious. Don't talk about it any longer. So at least people do not realize that you've done something as dumb as that. But I've never paid too much attention to what outsiders told me what I should be working on. I learned fairly early in my career to use my own judgment on these matters. Now, if outsiders told me that there was something wrong with my ideas, I would not necessarily dismiss this one. I would take a look and say, all right, let's see. But I would not base my decision on the reputation of the outsider. Whether this was another student or a director of a large electronics laboratory wouldn't influence my decision. I used my own judgment. I don't know whether I answered your whole question.
That was good.
Yeah.
Dr. Kroemer, I was interested in how you keep your creative curiosity vibrant at this stage of your career after all your accomplishments.
I don't know. I'm pleased that it still works. And in fact, I'm working now on things that are completely different from anything I've worked on in the past. So, as I said, I'm an opportunist. I'm looking for things that are fun to work on. And since I've been reasonably good at it, the fun keeps going.
I'm curious, it seems like you've spent a career sort of herding electrons. Have you developed a broader philosophical perspective of what they are? Or, I mean, in your own mind,
What the electron is?
How can you deal with not knowing what they are? Or how do you
Well, I know what they
think
are.
about
They have a certain charge, they have a certain mass, they obey in classical limits, they obey Newton's law and quantum mechanics.
beyond,
I'm obviously not answering your question, I know that.
beyond as constructs,
You mean philosophy?
more or less?
Not really. I mean, I'm acutely aware of some of the epistemological questions raised by quantum mechanics. They interest me, actually. But I try not to get too distracted in my practical work from those ones. Yeah.
Thank you.
Professor Kroemer, in your mind, what discipline in the sciences or engineering today is the most useful in acquiring these tools of innovation?
I don't know whether it makes a great deal of difference. I think all disciplines have this one, so if you're clearly not asking me what I would study today if I were a beginning student. I would obviously probably do something different from what I have been doing. But that's not the question you were asking. You were asking what disciplines. I certainly feel, but this sounds fairly standard what I'm telling you. I certainly feel that we have reached a stage where we can begin to answer some of the questions in biology. So I believe that there will be a lot of excitement in biology. And particularly, I think biology will be one of the fields where the much hyped nanotechnology will probably play an important role. But if you yourself are interested in something altogether different, I'm convinced that you find exciting problems no matter what the discipline is. I don't know whether you answered the question, but I tried to.
Professor, again, what are you working on right now?
What?
What are you working on right now, currently?
Right now, well, right this moment, I'm actually getting hungry, but the one topic that has intrigued me for a few months now is a phenomenon called negative refraction. How much time do you have? So it turns out that there exists. This is actually a very popular topic right now. It sort of burst into the open a few years ago. That you can have, under certain conditions, a medium can have a negative refractive index. And that raises and the conditions under which this raises all sorts of questions And an unbelievable amount of nonsense is being published about it. And I'm trying to be a troublemaker in this field because, for example, some of the claims that are being made actually, in my opinion, violate Maxwell's equations. And I don't like to violate Maxwell's equations. I'm not optimistic enough that this will work. So this is one of the things I'm working on. I'm also working on a topic called the Bloch oscillator. In fact, that Bloch oscillator is a direct outgrowth of one of the view graphs I showed you where things oscillating back and forth. I still believe that this can be used as a source to generate terahertz frequency waves without going to low temperature. So these are two areas of current interest. In recent years, but I've stopped working on that. In recent years, well, during the 90s, I did a lot of work on combining superconductors with semiconductors. So these are sort of the three topics that of recent vintage that I could mention. I'm absolutely not working on anything that is related to the stuff I got the Nobel Prize for. I don't think you. I've run out of ideas on that one. And you see, I rather spend 10% of the time to solve the big questions and spending 90% of my time to solve all the remnants. There's never a shortage of people who are only too happy to pick up the remnants. I'm not one of those. So you get stale if you work on a project for too long. So, now, this may come as a surprise to you because, after all, I've worked on semiconductors most of my career. To tell you the truth, I've been desperately trying to get out of semiconductors several times. It's just happened every time I tried to do this. Something absolutely exciting came along to which I felt I could contribute. So I actually didn't have a single semiconductor career. I probably had a half a dozen semiconductor careers that were distinct from each other. When I'm getting out of something, I tend to not pay any attention whatsoever to what others are doing. I remember I was working at one particular laboratory, and two guys came into my office. I had joined that organization, not only recently. Two guys came in my office and said, well, what do you know about the drift transistor? Oh, they wanted some questions. We have some questions about the drift transistor. Now, I decided I didn't want to answer questions about the drift transistor. I said, I know nothing about the drift transistor. So he pulled out the paper. Well, this must be a different Kroemer then. And so I've worked on, for example, on the gun effect for many years. 10 years, almost. I haven't the foggiest idea what's going on in this field. I get out at a certain point. I'm not saying that this is good or bad. I'm simply saying this is the way I work. Did I answer your question?
Doctor, I have maybe one final question for you. Do you have any insight as to how you can help link the technological world with the research world, and so as the research doesn't get lost in the labs, and just how does it really get implemented?
I don't know what you mean by this when the technological. I mean, to me, the technological world and the research world, they are linked, period.
How does it get into the business world?
Oh, well, I do believe that, well, first of all, you know my lemma. But this lemma, and you do know that I do believe that the most interesting applications of new technology are applications we created. But this tends to be a long-term proposition. And I do believe that the business world, for some very good reasons of their own, do not want to get engaged in things that are far away. The investment is big. The risk is very high because you do not know what's coming out. And on top of it, the profits from this undertaking very likely will go to somebody else. So I'm fully in sympathy with the business world's reluctance to support open-ended research. I get very, very nervous if I hear voices from the business world that try to tell us at the universities not to do open-ended research, but to do strategic research. And one of the reasons I get annoyed about this one is not just because I want to retain the freedom to do research. I believe that a university is ultimately in the business of education. And in particular is in the business of education at the top level. The real elite, the leaders in industry and business for the next generation. And in the sciences and in technology, actually participating in research where you do not know the outcome beforehand is the best, the most valuable piece of education that a student can pick up. And so I'm defending our right to do whatever research comes along, independently of whether this has any foreseeable application. I'm defending it because I believe I owe this to my students. Because this way, it is a wonderful experience if you are a student and get confronted with questions where you actually have to make educated guesses, where you have to make intelligent decisions on the basis of minimum inputs. It's an education in problem solving. It's an education in making judgments. And in the furthermore, there's another aspect to this one. Those people who do then go out will go to industry. They are the natural carriers of innovation in industry. So I feel very, very strongly about retaining the freedom to do open-ended research, at least in educational institutions. And I think I do this not just because it's in my self-interest. I can defend this on good grounds of national interest. How else would we have innovation?
Thank you, Dr. Kroemer. And once again, thank you to our Winter 2005 TMP Lecture Series sponsors, Shepard, Moeller, and Riker Vow, and Stradley Yucca. Thank you.